Thank you everyone for braving the weather today. It's very close to not making it in. The plows had blocked my street, and just a little patch that I was able to make it through. I was ready to record a lecture from home and ask somebody to play it here. Anyways, all right. So last week, first class, we left off. We were discussing sort of reductions of carbonyls, right? And one of the things that we sort of discussed was how if you have something like an ester, let's say this ethyl ester here, and we take this and we treat it with lithium aluminum hydride, you may assume that if you're going to add one equivalent of hydrogen across this, for example, right, what you would in principle get to with, based upon the mechanism that we had previously, right, is this compound here. So if we effectively add hydrogen across here, right, here would be our hydrogens, which is effectively the reduction. And what we sort of discussed, right, as we were discussing condensation chemistry, was that this is not going to be a stable intermediate. This is a hydrate, right? And a hydrate is going to rapidly break down, and what's going to end up happening is we are going to get to an aldehyde, right? As we also learned last week, aldehydes are far more reactive at reducing than, say, an ester or a ketone. They're very, very highly reactive, so as you can imagine in the presence of LAH, what's going to happen is you're going to reduce all the way down. Effectively, we're going to add another, in essence, equivalent of hydrogen followed by a clinch across there, and you'll get to this sort of primary alcohol. We sort of call this is the primary alcohol. Okay, so there's no stoichiometry that you could use that would prevent the reduction of an ester to an aldehyde. Some of you may say, well, what if I just added sort of one equivalent or 0.25 equivalents or something like that? Would there be a way that we control that? And the answer is no, because again, the reduction of this aldehyde is going to be so quickly. It's going to happen so quickly that if you have some of this in solution and you have some of this in solution, this is immediately going to react before that. So best case scenario, maybe you could get unreacted ester and alcohol. You'll never generate sort of aldehyde. So anytime you have an ester and you want to reduce that ester, what's going to happen is it's going to go all the way down to the primary alcohol. Now, the question is, right, so you're not going to get the aldehyde at all. You're going to get the alcohol. Now the question becomes, are there ways that we can reduce an ester and actually get selectively to the aldehyde? And there are ways. There are little tricks that we can do. And as you might imagine, we'll discuss this a little bit in terms of oxidation chemistry. The way that you could do this is by effectively preventing, right, the formation of that aldehyde. And so you say, well, if I want to generate an aldehyde, how would I prevent the formation of the aldehyde? And again, remember, this is all a process, and so we don't necessarily have to think about it as a single reaction. We can think about it as multiple operations. And the way that we historically are capable of reducing esters to aldehydes is using a reagent known as dibol. Sometimes it's called dibol hydride. What dibol is an aluminum-based reducing agent. With two isobutyl groups on it. So it actually stands for diisobutyl, DIB, diisobutyl, two isobutyls, aluminum hydride. Okay, so this is dibol. Now if you look at dibol, you look at some of the differences between dibol and, say, LAH, you'll notice that this sort of net charge on the aluminum is actually neutral, right? Unlike in the case of lithium aluminum hydride, where we effectively have that aluminum or aluminate, right, in the negatively charged state. It's all ready to take its hydride and sort of reduce. In fact, if you have dibol, you often buy dibol as a solution in something like hexanes. It can exist as a dimer to sort of meet its coordination state. Sometimes it's drawn. Sometimes you'll actually see it like this. right, where you have like sort of interactions between all of these sort of dimerization states, and that's not super, super important, but some of you may be saying, well, you know, we've got this really strong Lewis acidic site and wants to have those 8 electrons, and so there's ways that it can do it based upon sort of this dimerization process. Now, in a solution, in a reaction, in order for this to behave, right, as a hydride, in order for an H minus to be able to be generated, we need that aluminate, right? And this is one of the things that happens in a Dibol reaction, is that in order to get that aluminate, right, we have a really good Lewis acid, right? On our carbonyl, right, we have lone pairs, which are Lewis basic. Okay, and so the first step in a Dibol reaction is, in fact, coordination. Of the aluminum to the carbonyl. Okay, so the lone pairs on the oxygen are effectively going to attack, right? We effectively now fulfill the octet of aluminum, and through that process generate the aluminate, right? And so now what we have is that charged species, your aluminum-hydrogen bond, is now much more similar to what it would be in something like LAH. And in an intramolecular fashion, what happens, again, there's perhaps the mechanism is a little bit more complicated than this, but what's going to happen is we're going to get that intramolecular delivery of that hydride source. Okay? Okay, when we do that, we are left with is this sort of aluminum coordinating species. Now, as it turns out, the mechanism is going to be a little bit more complicated than this, but I think perhaps the way to sort of think about this reaction is that this is different than this. Why? Because you effectively now have an oxygen-aluminum bond, right? You're not as easily going to sort of break down, right, to leave ethanol. And the other factor about this reaction is it's held at a very low temperature, minus 78 degrees Celsius. This is dry acetone, it's really, really cold. So you keep this temperature very, very cold, and at these low temperatures, this is stable. Okay? So if you slowly add Dibol at low temperatures to an ester, what will happen is the reaction will lead to this intermediate here, okay? And then what you do is you add water to this solution. The water is going to quickly and rapidly quench if there's any leftover Dibol. Generally, you try to be very specific with the Dibol. You try to use one equivalent of the Dibol. But if there is any extra Dibol in there, you'll quench it with the water. And during the aqueous workup, what's going to happen is you're going to degrade that aluminate. You can imagine water adding in, eventually getting to hydrate. Right, and now there's no more Dibol in there, so when this breaks down, you end up getting the aldehyde. Right, cleanly. And again, at this point, you've quenched all the, while you're also sort of helping break down the aluminate species, or the sort of oxygen-aluminum bond. While you're done with that, you're also simultaneously quenching any extra LEH. So in this case, what you can actually do is control this process. Use Dibol and get directly to the aldehyde. Okay, so this is another option if you want to reduce specifically from the ester. Now we have a couple options. If we want to go all the way down to the alcohol, right, we can use LEH. If we want to go to the aldehyde and stop at the aldehyde, we can go through this sort of Dibol-mediated mechanism. Okay, so again, these are structurally very similar in a way, but the big difference here is your alumina isn't set up as a hydride right away, right? It needs to coordinate first with the carbonyl before it can actually behave in this fashion. Okay, so this is a Dibol reduction. Okay. All right, so in addition to the sort of reductions that we've seen to date, in all the cases that we've seen so far, right, with carbonyl reductions, we've seen them go to, in some type of way, we've seen them go to, I'll just say, X to represent the different things that we have, right? What we've seen is sort of hydride, then, right, proton source of some type, formally adding hydrogen across that bond. Right? In this case, what happens, again, there could be other things that can happen, but formally what we're doing is adding hydrogen across that carbonyl bond. Again, it can be degrade and then reduce again in cases like esters and so forth, but in general, this is what we've sort of seen. And again, there are analogies between this and, say, for example, alkenes, right? And so as you might imagine, there is chemistry where you can do similar reductions of carbonyls without this hydride followed by protonation state. And so another type of reduction that you can do, right, is actually just do hydrogen and some type of a metal, right? So you'll have a balloon of hydrogen gas, and there's certain metals that will actually reduce this. So the book will just sort of use generic metals, but metals are all different. I think the book says platinum, palladium, right? There's lots of different metals that will do this, rhodium and so forth. And so it's oversimplistic to simply say, oh, platinum will do that, because platinum, you know, usually it's some type of hydrogenated source, platinum oxide or whatever. But the important point is if you were going to do the reduction, you'd probably look up the metal source anyway. But again, we've seen similar chemistry to this with alkenes, right? We see palladium and hydrogen reduce alkenes, and so as you can imagine, certain metals and hydrogen would also reduce these as well. Right, so that's one thing that you can do. As you might imagine, if you were to do this chemistry, there's sort of selectivity issues, right, where let's say you had a molecule that had an alkene and a carbonyl, right? This might be an instance where you want lithium aluminum hydride if you want to selectively reduce the carbonyl, because if you treat it to these conditions above, right, what's going to happen is you're going to reduce the alkene and the carbonyl. Right, so you're going to end up reducing both of those. And so this is one of the advantages, say, for example, to having lithium aluminum hydride or sodium borohydride is that you can selectively reduce the carbonyl. In the case that I've shown, there's modifications to this called sort of a loose reduction. But the point being that these sort of hydride methods can often be a little bit better in terms of if you want to gain selectivity. Now, another question would be, again, what if I want to reduce selectively an alkene in the presence of carbonyl? Again, the book uses a very oversimplistic sort of way to sort of say that you can do this. It sort of says, oh, rhodium and hydrogen, which is, again, not entirely true. But I think the more important point that the book is trying to make is that there are metals out there that can be used to reduce, say, for example, an alkene in the presence of a sort of carbonyl. And again, depending upon the source of the metal, this is a little oversimplistic, but whatever, run with it, right? And so if you want to selectively reduce an alkene in the presence of sort of carbonyl, you can imagine using rhodium. If you want to reduce a carbonyl in the presence of an alkene for a synthesis type question, you could use LAH or sodium borohydride. And if you want to reduce both of them, you could use something like platinum or sort of palladium. Okay? So I just wanted to make that clear. All right, so in all these cases, what we've done is we've reduced the molecules to alcohols, right? And what we've formally done is added one equivalent of sort of hydrogen across these. I'm going to start over. a little bit. It's sort of one of the things about oxidations and reductions, right? Does anybody know where the sort of terms oxidations and reductions formally come from? I mean, I guess it's kind of a broad question, but you guys ever heard of like oil rig? Yeah.
Oxidation numbers?
Yeah. Right. What we're kind of talking about is the sort of electrons, right? So you guys might have heard oil rig, right? Oxidation is loss, reduction is gain. Formally, what we're talking about is right, and sort of when we talk about metals, perhaps it's a little bit easier to think about the oxidation of metals. When we start thinking about organic molecules and things like reductions and oxidations of carbonyls, there can often be some confusion in terms of what an oxidation means or what a reduction means. And so I'll just make a point real quick. I think this can be confusing, but hopefully I can make... What we're talking about here is electrons. Okay, so if we're doing a reduction, like what we just saw, right, what we're doing is we're adding electrons to this system, right? So if we're adding, say, for example, hydrogen across these bonds, we're not only adding 2 atoms of hydrogen, but we're not only adding the 2 protons, but we're adding the 2 electrons that come with it. So we're effectively reducing this molecule, but in principle, what we're doing is gaining 2 electrons in the overall system. So if we just think about the net result of this process, right, we are gaining a couple electrons through the hydrogen. And I think this can sometimes be confusing because what we're really talking about is the overall process in a way. And I think where it can sort of particularly become confusing is as we start to talk about things like reductive or exhaustive reductions, which I'm going to get to in a moment, which is one of the reasons I bring this up. And then subsequently we'll talk a little bit about oxidation and how the sort of the reverse can oftentimes be confusing when we hold this as true. So I think it's just one of these things that I always thought is sort of interesting to think about, why it's called an oxidation, why it's called a reduction. It will eventually translate to things such as metals, but that's formally what we're talking about, is the electrons, right? And again, you guys learn about oxidation and reductions probably in high school, but we're really talking about metals. Here we're talking about sort of the formations of sigma bonds. Okay, now, if we, say for example, take a molecule and we do what we call an exhaustive reduction. And we'll give a few examples of these. What we mean is we're going to reduce this really all the way down to the alkene chain. Okay, so and we'll discuss technical ways in which we do this, but an exhaustive reduction, when I refer to an exhaustive reduction, what I mean is that I'm not only going to reduce to the alcohol in principle, but I'm also going to basically fully saturate that bond, put all the protons there that I could possibly have. So this would be called a sort of an exhaustive reduction. The thing that might be confusing about this is that when you just look at the 2 atoms here, you might not really see, well, where are we gaining the electrons, right? But it's important, we'll see this with oxidation, that we consider the overall process, that what's also being gained here and what's also in here is water, right? So water would, say, for example, be a byproduct of this, so you're adding effectively hydrogen to the system, and so yet the overall sort of net process, right, you could think about as the sort of water as well. So we're picking up electrons in this process when we consider it as sort of water. Again, that's just nomenclature. I think that makes things more confusing. Forget it. But I think it sort of at least simplifies the names to me, and perhaps once we start talking about oxidations, this will come true as well. So a reduction at its core doesn't necessarily mean, say for example, add hydrogen to a system. It's really adding electrons to it. So what are some examples of exhaustive reductions. So there's really two that we're going to learn. The first one we're not really going to discuss the mechanism of because sort of more metal-based, and we'll get into organometallic mechanisms down the road, but I think for now, this is just a reaction that you're going to want to know. And again, anytime you learn a new reaction, I think it's best to sort of compare it to things that we've seen in the past. And so in many ways, a Clemmensen reduction basically take this zinc mercury amalgam, you treat it with HCl. Formally what happens is you make a hydrazirconate, so it's sort of like the zirconium exists as sort of this hydride source, so this will effectively insert in this sort of zinc, sorry, I keep saying zirconium, zinc mercury amalgam, not zirconium. So it's a hydro zinc, I don't know what the name of it would be, but basically the zinc inserts into the hydrogen fluoride bond. The net result here is you get the reduction, full reduction. So again, the mechanism of this one's a little bit more complicated. I'm not going to make you guys responsible for sort of knowing that, but this is one reaction that you guys should know, so it's an exhaustive reduction. The more complicated mechanism that I will hold you guys responsible for is the Wolff-Kishner reduction. And there's a few things about the Wolff-Kishner reduction that I think are interesting. This is one of the, I think, more sophisticated mechanisms that you guys would want to know. It's certainly one of the ones that is a little bit more of a struggle to sort of learn. So I'll show it over here, and then we'll discuss the mechanism over here. And a Wolff-Kishner is a two-step process. Okay? And the first step is that you take a carbonyl and you condense it with hydrazine. Okay, hydrazine is basically like the nitrogen equivalent of hydrogen peroxide. So it's nitrogen-nitrogen bond with hydrogens around it. Okay? Now, this condensation reaction actually will happen without any acid or whatever, but from a mechanistic standpoint, since a lot of the condensation chemistry that we've seen to date, in principle, involves sort of some proton source initiating it, I think from a mechanistic standpoint, I think it's perhaps, even though it doesn't work like this, I think it's best that you guys sort of think about some sort of proton source. Again, because when you guys are thinking about mechanisms, I think it's oftentimes a good idea, right, to not necessarily generate separations of charges. So you can think about this process taking place with a proton to sort of help catalyze the process. That should make perhaps things a little bit less confusing, because it's within the realm of condensation chemistry. We'll discuss this mechanism in a moment, but what's going to happen is this is going to involve a condensation of an amine. This is something we haven't discussed yet. We'll discuss in a moment. I kind of wanted to hold off. Yes? Okay. Okay, so what we're going to do is we are going to condense the carbonyl with hydrazine. Okay? And then what's going to happen is we're going to take this compound and we're going to treat it with sodium hydroxide. And again, we'll discuss this mechanism, but this is going to end up leading to our sort of reduction. So carbonyl, this is what we're going to call the nitrogen-carbon double bond, is an aminium. I'll redraw it over here, so hopefully it'll be easier to see. But again, it's a two-step process. Now, the first step is condensation chemistry. And so again, this is chemistry very analogous to the very first reaction that we learned. Okay, so it's probably best to think about this in sort of two parts. And so the first step condensation. And again, hydrazines are kind of special. They're really good nucleophiles, so actually you don't really need a acid in this, but I think from a mechanistic standpoint, we'll just sort of use a little bit of acid to sort of think about this mechanism, right? And so as we learned before, the first step in any condensation reaction, I was going to start with protonation of the carbonyl. Why is it protonating the carbonyl, you ask? Why wouldn't it protonate the amine? Well, certainly it probably could. But again, that's reversible, and it's not going to be a productive pathway. So over time, what you'll end up doing is we'll protonate the carbonyl. And now, once you've activated the carbonyl as an electrophile, what's going to happen now is the hydrazine can add in. Okay, so the hydrazine now going to add into that species, okay? Charge now, right, sort of moves over to the nitrogen again because that nitrogen is now going from owning that lone pair to now sharing it, so it goes to a positive charge, okay? We'll do a proton transfer. Again, this can happen either with, say, other molecule around, but just to save board space, what we will do is we will protonate it just in this sort of intermolecular fashion. Okay. Once we do this, what's going to happen is now we've got water as a leaving group. Again, that's where the name condensation comes from, right? Condensation, water, loss of water. Or gain of water, I actually don't know. I guess maybe the system generates water. Maybe that's where the name comes from. But what we're talking about here is in essence, the loss of water from the system, gain of water perhaps into the environment. Right? Now we have our sort of iminium. And again, what can happen here, I just sort of had it as a proton source before. So in this way, we can sort of regenerate the acid. But again, the H plus is probably some conjugate base associated with it, which would then go and deprotonate it. But the point being that now what we have is our imine. Okay? Now, this is going to come up again. You guys should know this condensation of amines, carbonyls, very well. Okay, we'll discuss it a little bit later, perhaps today, later on today if we have some time, but this is going to be an important step in enolate chemistry, so I think I might hold off on discussing imines until we get into that. So that's going to be the first step, okay? This one you guys should be able to get. I would expect all of you to be able to do that. And the second step is going to be this base-mediated I guess you want to call it a sort of a base-mediated reduction, I guess, rearrangement. Okay, so the second step in this process is going to be take this reaction, you treat it with base. Okay, and we're going to sort of reduce this species here. Okay. Now, how does this work mechanism? Now, this is perhaps a little bit more challenging and not obvious of a mechanism, so it's one of those ones that I think could become a good mechanistic problem to try to figure out on your own. We'll go through it though. And there's not necessarily a single right way to draw this mechanism. There's a couple different ways that you can imagine this mechanism. But if you think about the overall process, right, what we need to do is we need to get hydrogen here twice, right? And through this process, we'll see we actually will generate nitrogen gas as a sort of a leaving group, or it's not really a leaving group per se. But the way that I often think about this first and foremost is, do you guys know what tautomers are? Did you guys learn about tautomers last semester? Okay, so for those of you who aren't So sure about tautomers. Carbonyls, for example, can undergo rapid tautomerization. It's effectively, kind of in a way, not really, but sort of like a resonance form. But they're not resonance forms, so they're actually different compounds. There's a hydrogen that sort of moves throughout the system. So if you have, say, for example, a hydrogen here on a ketone, as some of you guys know, there's these things called keto-enol tautomers. Minor resonance form, where the hydrogen that's out for the carbonyl actually ends up on the oxygen of the carbonyl. And so protons can actually move fairly readily throughout systems like this. Again, it's sort of reversible in this case. These are called tautomers. And so anytime I think of the Wolff-Kishner, I often like to sort of simplify the mechanism a lot if I just think about a tautomeric form of this. And so, again, we sort of see this tautomeric form here with the keto-enol tautomer, which some of you may be familiar with. Did you guys learn about the keto-enol tautomer? Great. So now what I'm going to do is I'm going to draw the analogy here. If I just sort of flip this over a little bit. All right, we can sort of view this hydrogen as being this hydrogen, right? And that carbon there sort of being the carbonyl. Okay, everybody see that? So you have a double bond, sigma bond, proton. Double bond, sigma bond, proton. And so as it turns out, you can sort of see a tautomeric form of this compound as well that's very analogous to the keto-enol tautomer, where this proton is going to end up on this carbon, right? And then you're going to have a double-double bond here. Do you see that? It does, I don't know it. But this is just a tautomerization. It's not as prevalent as the keto-enol tautomer, so I'm not sure that it has an actual name. But it's going to be the first step. Okay, you can at least think about this as the first step, and I think that this often simplifies this problem fairly quickly. Because once you can get to this tautomeric form here, which I will simply redraw, you see that this puts one of the protons that you have over here on this system. Okay? All right, so just by doing the tautomer, we get one of the protons there. And again, this is going to be reversible in principle. And now what we can do is we can bring that base into this system here. And as you might imagine, again, we've got a couple protons that might be able to be taken off, but certainly heteroatom protons can undergo deprotonation. I'm going to erase this, so I'm going to need forward space. But if the base can deprotonate that hydrogen, right, what we will have is a nitrogen with a negative charge on it. And this is where I think we get to an intermediate that on the surface might seem a little bit difficult to sort of visualize, right? Because generating alkyl sort of anions, carbon-based anions, is not necessarily something that we've seen a lot, right? You would imagine that's a very high uphill barrier to be able to sort of generate that negative charge. But the way that you can sort of justify this, right, is that you're losing nitrogen gas. And so every reaction is in principle a little bit reversible, right? But the fact that you're generating a gas renders this process here completely irreversible, right? Because it's a gas, it goes away. So even if it's only a minor equilibrium towards this anionic form, it's all going to go that direction because your nitrogen is going to go away. And then obviously once you're here, right? You can pick up the proton, and we're basically fully reduced. All right, so we've got water generated previously, so we can imagine using that. Right, and that's going to give us our reduction. Okay, so I think it simplifies it remarkably. If you can see that tautomeric form, if you have to sort of do a deprotonation, resonance form, reprotonation, you can certainly do that as well, and you can go through that on your own. But I think as you can sort of see the tautomer, right, that I think simplifies this sort of mechanism very, very well. Okay, so this is a reaction you guys should know. You should be comfortable. It's certainly one of the more complex mechanisms that we'll learn in Organic 1 and Organic Chemistry 2. But again, it's one that I think you should all definitely know. All right, so these are the reductions. Okay, so reduction is gain of electrons. On the other end, what we want to discuss a little bit is sort of oxidation. Now, did you guys discuss oxidations last semester? Okay, well, we'll discuss them really quickly again, just to sort of bring this full circle. But I'll try to be fairly quick with it. And I'll make one point that may or may not have been brought up previously that I think might help make sense in the same way that, say, Divol makes sense at the chemical level. I think there's certain aspects of oxidation chemistry that are sort of interesting. And so, as sort of reductions are the addition of hydrogen effectively across here, you can imagine that oxidations are kind of the sort of loss of those two protons associated with hydrogen. And so, right, formally hydrogen of some sort is sort of lost from the system. So you've effectively taken 2 electrons away from this process. This is why it's a sort of what we consider a loss of electrons in a way, okay? And I think there's really 2 oxidations that you guys should know, and they're both sort of chromium-based. Okay, and the first one is chromic acid. Now again, you're not going to be held responsible for mechanisms until we begin to talk about organometallic chemistry. I'm not going to necessarily hold you guys responsible for organometallic-based mechanisms. But I think it's worth it to sort of discuss intermediates within this sort of context of losing hydrogen, right? And so chromic acid, Jones reagent, basically you take CrO3, sulfuric acid, generally run this reaction in acetone and water mixture. It just sort of solubilizes the organic species. What happens in sort of the Jones reaction, as you guys, sounds like you guys know, right, is that you can take carbonyls and effectively oxidize them. So it's chromium-based. All right. So if you have a, say, secondary alcohol, such as the one that I've shown you here, what you're going to get to is a ketone. Okay. Now, turns out, as I guess you guys also already know, right, that if you do the same thing with Jones reagent, right, with a primary alcohol, what's going to happen is you're not going to get to the aldehyde, right? You're not going to be able to stop at the aldehyde. The reason is that this is such a strong oxidant, in the presence of something like water, right, what's going to happen is you're going to generate what? Hydrate. right? Okay? And so what happens in this process is once you're at the hydrate, you have the ability to lose a second equivalent of hydrogen. So here we lost our first equivalent of hydrogen. Right? Once we make the hydrate, we're in a position where now we can actually lose the second equivalent of hydrogen, or the electrons associated with this other compound over here. Right? And that's going to lead us to carboxylic acids. Okay, so much in the same way that you can't control a reduction, say, of an ester all the way down to an aldehyde, right? The aldehydes are very reactive intermediates. So it's often difficult to stop it halfway in between. You need some sort of tricks to play. In the case of chromic acid, if you take a primary alcohol and you oxidize it with Jones reagent, what's going to happen is that you're going to get to the carboxylic acid. Same way in the reverse, if you take an ester and you treat it with LEH, you're going to get the primary alcohol. So stopping molecules from those intermediate aldehydes can sometimes be a little difficult. Now, as it turns out, I think that in the case of sort of the LEH reduction, I think perhaps it's a little bit more difficult to see how that might have been found. But if you sort of look at this process here, right, and you look at why the aldehyde, say for example, is going to further oxidize, the whole reason comes down to the fact that you're running this reaction of water and acetone, right? If you can, in principle, stop this reaction from generating the hydrate, then you should be able to stop the molecule oxidizing at the aldehyde. Now the issue is, right, is that these reagents, chromium trioxide, sulfuric acid, it's very difficult to get them to dissolve in organic media. This is one of the reasons why this chemistry is run in sort of acetone water. And so you guys have learned about PCC, it sounds like, right? But really what is the only real special thing about PCC, so PCC is chromic acid plus HCl plus pyridine. Right, you mix these two together and what you get to is pyridinium chlorochromate. Okay. So this is pyridinium chlorochromate, okay? PCC. Okay? And what PCC is, formally, is an organic soluble high oxidation state chromic acid species, or sorry, chromate species. Okay? And so what this allows for you to do is run this reaction in dichloromethane. This means that you can basically use PCC on primary alcohols. PCC is generally run in CH2Cl2, and usually, actually always, you run it over some type of a desiccant, right? Something that's going to absorb any water that might be around. The desiccant is generally molecular sieves. I don't know if you guys have heard about molecular sieves. They're just porous sort of materials. You can use 3 angstroms or 4 angstrom molecular sieves. What that's going to do is that if any water might be in there and the adventitious water, it will sort of keep it away. And this will lead selectively to this sort of aldehyde. And so as you might imagine, if you add water to the system, it's going to kind of defeat the purpose. You'll probably get the acid as well. Okay, so chromic acid, Jones reagent per se, and PCC. So these are the two oxidations that you guys should know. All right, we're making good time. All right, I'm going to discuss, now I'm going to discuss a reaction that I think is a pretty cool reaction. It's another perhaps mechanistically complicated reaction, one that's certainly powerful. So again, we've discussed oxidation, we've discussed reductions. We've discussed nucleophilic addition to carbonyls. But there are a few other reactions that we're going to want to learn before we begin to move further a little bit more. Okay. The reaction we're going to discuss right now is the Wittig reaction. Okay, and a lot of the reactions that we've learned to date, again, have sort of been the reverse of reactions that we've seen in the past. So oftentimes, I think it can be confusing sometimes, especially when you're trying to learn retrosynthetic analysis, to suddenly throw in reactions that can go in multiple ways. But again, by the same extent, really what we're dealing with a lot of these reactions is interconverting different functional groups, right? And so sort of understanding what type of reactions are available to go in different directions from given compounds can be important. And so we know previously, right, that if we take alkenes and we want to generate carbonyl, how do we do that? Ozonolysis, right? So we know that we can go in this direction. So that's last semester, so usually it's ozone followed by some reducing agent, either zinc or DMS. You can also go in the reverse direction, and this is going to be a process that we're going to learn right now, called Wittig reaction. Okay. The way that a Wittig reaction works is that you take a carbonyl species and you treat it with some type of a phosphonium salt. Okay, so we haven't really seen phosphonium salts that much. The process involves these molecules which we call ylids, YL. An ylid simply refers to organic molecules which have a positive and negative charge associated with one another that are sort of usually adjacent to one another in terms of charge. A little bit different than, say, zwitterions. So ylids are generally referring to molecules where you could otherwise perhaps draw pushy electrons and actually sort of, as much as you can imagine as being a double bond, it's fine if you draw the double bond as well. But it turns out there's not really a pi bond associated with that, so it might not necessarily be the most accurate way to draw it. And again, looking at the mechanism of a Wittig, perhaps easier to think about it in this ylid form anyway. So we'll just draw it as the ylid form. And what's going to happen, and again, it's going to depend upon, I'll just draw a squiggle line here for now. But what happens in a Wittig reaction is that the component that's over here, right, ends up on this carbon here, and the byproduct that you generate is triphenylphosphine oxide. And so we'll discuss the mechanism of this in a second. But again, the idea is that sort of this half of the molecule reacts with the other half, the sort of the blue circle on one side reacts with the sort of blue circle on the other side, and you sort of get a double bond. And again, there's a possibility for olefin isomers there. You can either get E or Z, and we'll sort of discuss some of the selectivity that can often be attributed to these in a moment. Now the mechanism, I don't think it's the most complicated. It's actually a fairly straightforward mechanism. It's not the longest mechanism in the world, but I think it's a little bit different than perhaps you guys have seen in the past. A couple of years ago when I taught this course, I went into a lot of depth on the Wittig mechanism, and I realized it was probably just a mistake. So if you guys want to know more about the sort of details behind the EZ, I'll discuss a little bit about the EZ selectivity, just to sort of give you guys some guidelines if you want some mechanistic rationale behind it. We can talk about it in office hours or one-on-one or one-on however many you guys want to know about it. But formally, the reaction is, we're going to see this again in a reaction known as a metathesis reaction. formally what the process is kind of in a way a sort of a 2 plus 2. Okay, so we're going to make the oxygen, again, phosphine is not the same level as carbon, right? So we can actually break the octet rule on aluminum, silica, phosphorus, sulfur, again, because they can pull upon their d electrons. So that might look a little uncomfortable at first, having 5 bonds to something, but remember this is a different row of atoms. And so what happens in this process is you generate cyclic structure here. Okay. And then what's going to happen is you're just going to break down this sort of species. So again, if you want to draw it as a sort of double bond, you can. Again, these are simply just resonance forms of one another. Usually this is drawn this way. Again, it's the difference between the illid and the sort of double bond, so either one of those is fine. They're just resonance forms, although this one is the more accurate representation of it, but I'm not going to get upset if you draw that one. Right? And then again, then the product that you're going to get is the sort of alkene. So it's a fairly quick reaction, just sort of 2 steps. Again, we're going to learn a reaction, a metal-based reaction with a metathesis reaction. It's mechanistically very similar to this. Richmond Sarpong at Berkeley had a video. I guess he posted this video where he had a couple people, like 4 people, come up and they did the Vidig dance. They went around in a circle, and I don't know, it's kind of funny. We don't have time to do the Vidig dance here, but maybe I'll post the video for you guys. So anyway, so this is the Vidig olefination. You can think about it as being the carbon-based nucleophile adding into the carbonyl, the oxygen making a bond with the phosphorus, generating this 3-membered cyclic structure, which degrades to generate the alkene in this compound over here. Now, the selectivity here, we can have E or Z double bonds. There's another reaction I'm actually not going to discuss. I think it's a little redundant. That's the Horner-Wadsworth-Emmons olefination. It's actually a really useful reaction, but I think it's probably just redundant to discuss the Horner-Wadsworth-Emmons. But it's mechanistically very similar. It's in your book. I'm not going to go over it. But anyways, your E and Z double bonds that can form, turns out that the reaction is selective. And it's going to depend upon what the sort of R group is over here. So if the R is a proton, it doesn't matter. It's very common that people just simply do a Vidig olefination to generate a terminal alkene. So if R is a proton, it'll just generate the terminal alkene. That's actually useful. A lot of people use that. But if you have some type of a group here, what you generate is going to depend upon what the sort of nature of that R group is. And so I'll try to teach this to you guys as succinctly as possible. Let's discuss a couple of different types of R groups. Okay, so here's 2 different possibilities of R groups. Okay, the top one is just a methyl group, right? The bottom one is an ester. When you guys look at these 2 illid forms, if you had to guess, again, it's not right or wrong answer. I'm just kind of curious. Well, there is a right answer, but I don't necessarily expect you guys to get the wrong answer for what would be a rational reason. I think that's fine as well, but we'll discuss this anyways. Of these 2, which would you think would probably be more stable? All right, and why? Yeah, right, so in the bottom case, what you have is a negative charge alpha to a carbonyl. We're going to discuss this a little bit. This is actually an enolate in a way. It's resonance stabilized, right, into the carbonyl, but you have this resonance stabilization to this carbonyl here that you don't have over here. So this is what we would call a stabilized ylid. Okay? And in the top case, it's what we would call a sort of unstabilized ylid. Okay? And as it turns out, whether a compound is stabilized or whether it's destabilized, you're actually going to get to two different products. And there is sort of mechanistic reasons behind this. That again, one time I tried to explain it, it was a disaster. So I'll just try to give you guys, the trend, try to give you guys a way to rationalize the trend, and then if you guys want to discuss a little bit more in depth with the mechanisms, we can do that sort of offline. Okay. Okay, and so the trend basically is that if you guys have, if your ylid is unstabilized, you actually get to the higher energetic species, the Z alkene. Which you might imagine again, the Z alkene, right, is going to be higher in energy, right? The two groups are close to one another, so this is higher in energy. If you have a compound that is a stabilized ylid, you're going to get to the sort of more stable the more stable E alkene shown here. Okay. Now, from a standpoint of rationalizing this, again, without going into depth in the mechanism, the reasons behind this have to do with thermodynamic versus kinetic controlled processes. Okay. As it turns out, well, there's actually not so new, it was a while ago, but when I was in graduate school, a paper came out, shows my age, that basically changed the viewpoint. But for a while, the way that people rationalized this selectivity is that it turns out the approach of either one of these into the carbonyl happens to approach in a way that when you go through this cyclic structure here, the lowest energy approach following the rearrangement actually leads to the Z. So again, show that in more detail offline if you want, but the idea is the approach that's lower in energy, when it actually rearranges, will lead to the Z compound. The reason why you would lead to the Z compound is if that first approach was then irreversible, not allowing it to sort of go in reverse. If it adds, you have to sort of rotate around, and you eventually get to the Z compound. In the case of a stabilized ylid, even though it would have the same relative approach at the beginning, the subsequent rearrangement is uphill enough that it doesn't go to the product. It will actually go in reverse. The energetics are low enough to go in the reverse because this is more stable. It will eventually go through the higher approach, which then becomes a lower in energy sort of rearrangement, which will eventually get to the E. So again, that's probably confusing, but the way you can sort of think about it is stabilized ylid, stabilized alkene. Unstabilized ylid, less stable alkene. And if you can sort of remember that trend, and if you want to learn a little bit more about the reasons behind it, we can discuss offline. Okay? Okay. All right, well, I just got through everything that I planned, and so I guess we have a little bit of time to discuss and move forward. All right, so this is the Vittig-Gold thing. All right, so a lot of the chemistry that we discussed involved again, relative reaction from carbonyls. Some type of functionalization, say for example, the nucleophile, right? This is the sort of trend with a lot of the chemistry that we had. Turns out that there's a lot of analogous chemistry that can be run through a sort of derivative of carbonyls called imines. Okay? And so, as we discussed with hydrazine, amines primary amines specifically, and we'll discuss what can happen with secondary amines in a minute, but you can condense primary amines with carbonyls and get the molecules known as imines. Okay? Imines are basically the nitrogen-containing cousin of the carbonyl. A lot of the chemistry that you can do with carbonyls, you can also do with imines. So if, say, for example, you wanted to treat an imine with, say, for example, cyanide, right, which is one of the things that we saw previously. This overall process is actually a well-known reaction. You'll add cyanide with these compounds. Drucker. Bless you. Okay, so you can actually add cyanide into these species. It's actually a really valuable reaction because, as it turns out, you can take these cyanides and you can hydrolyze them. It's actually a reaction we'll learn in a little while, but I'm sure you could probably come up with a mechanism for this. It'd be a good mechanism problem regardless. Okay. And what you have here are molecules that we'll learn a little bit about later on in the semester called amino acids. Okay, so you guys have all heard of amino acids. These are amino acids, and so obviously amino acids are natural, right? They make up all our proteins in our bodies. But say, for example, if you want to do chemistry and generate unnatural amino acids, and there's lots of reasons why people want unnatural amino acids, you can generate them through making imines, reacting with cyanides, and then hydrolyzing them. Okay, so this would be a good mechanism problem. But as you might imagine, there's other reactions that you can do as well. And one of them is actually really valuable, and there's a reason why it's valuable. And it has to do with just simply synthesizing amines, right? Amines are valuable functional groups, okay? But if you were to say, for example, take an amine, let's say that we wanted to take an amine, such as the one that I've shown here, and I wanted to treat this some base, right? All I want to do is functionalize an amine. Now, you guys have seen lots of chemistry with amines, right, where these molecules can serve as nucleophiles, right? And so you might imagine a mechanism where you could take this, treat it with, we'll make this one R1, we'll make this R2. You might imagine a reaction where all you want to do is that reaction there, okay? So obviously, synthesizing amines are very valuable functional groups. I think like 90% of drugs on the market have some amine in them. So you can imagine synthetic chemists that are medicinal chemists would want nitrogen and to be able to synthesize molecules that have nitrogen in them. And so this would, on the surface, seem like a really valuable reaction, but as it turns out, it's very difficult to control the synthesis of this, in part because the molecule that you make still remains fairly nucleophilic. And so you may generate some of this, but you'll also generate some of, say, for example, this. And in fact, you can also generate the ammonium salts as well. And so really, it's a mess. You get all these different possibilities. right? You get some mixture of all of these combinations. So it's very difficult to take an amine, treat it with something like an electrophile. Again, this would seem pretty standard, right, in terms of the chemistry that you guys know. All right, amines, good nucleophiles, right? Treat it with an electrophile, that should be no problem. But there are technical issues with actually running this in a lab. And again, they have to do with the fact that this remains reactive, can then make this, and even this tertiary amine, while a little bit less reactive, sometimes you can even get to compounds like that one there. However, so if you want to do primary amines, this is not going to work out too well for you. But using some of the chemistry that we know, you can do this. Just not with an alkyl halide. What you do is you're going to take this molecule, and instead of treating it with an alkyl bromide, what you'll do is you'll treat it with carbonyl. Okay? And do the first step, which would be a condensation reaction. Okay? And imine is going to be, again, you don't have alkyl halides around here anymore. This obviously isn't going to condense with another equivalent of aldehyde. Might add in, but it's obviously that's going to be reversible. And so what you can do is you can effectively do this first reaction, which is an imine condensation. Again, you guys should all be able to show the mechanism for this. We sort of went over the analogous one with hydrazine. And then all we're going to do, right, is simply add in a sort of a hydride source, right, as we sort of saw previously, right? And in this way, you can generate this molecule here. Okay? Now the hydride source that's the sort of go-to in this chemistry is actually sodium cyanoborohydride. So I'm not entirely sure what the need for sodium cyanoborohydride is for this reaction, but I guess it's just a little less reactive or something like that. Again, from a standpoint of you guys and the sort of a knowledge base here, you know, if you guys went ahead and said, just remember sodium borohydride, that would be fine as well. I really don't think that, you know, I think what's more important is you recognize that there's a reduction here. And that through basically a condensation reduction, you can be there. And so if you want to learn sodium cyanoborohydride as the reagent for this, that's fine. If you want to just choose to use sodium borohydride, I don't think your knowledge base of organic chemistry really suffers all that much by only knowing sodium borohydride. But this is the one that your book will discuss. It's the one that people have optimized towards. But again, I don't think there's any real rational reason why you guys should know that you need to use that one. So. Okay, so this is another example of sort of chemistry that you could do with this sort of a condensation. Okay, we're going to discuss one more sort of derivative of the condensation reaction, and then I'll let you guys go. So if you do the condensation reaction, right, with a primary amine, what's going to happen is you're going to use an imine, okay? But so this is just, I don't know, it's faster with these than with the carbonyl. All right. Now, if your amine is now, say, secondary, right? And when we say secondary with amines, it's a little bit different than like secondary with alcohols. Because amines have the ability to be monosubstituted, disubstituted, trisubstituted. There is some nomenclature difference to how we refer to amines relative to how we refer to alcohols, say, for example. The amines, when we're talking about a secondary amine, what we're talking about is substituted twice on the nitrogen. So this would be a secondary amine. So yeah, that can be confusing when we start thinking about alcohols. Now, if we take this molecule and we treat it with an aldehyde, or a ketone of some type, what we're going to get to now is an aminium. Okay, so this is a positively charged nitrogen. We'll discuss this a little bit, maybe later on in the course, discussing how aminium catalysis is often used for people to activate carbonyls with secondary amines. For the point of this course, it's important to recognize that aminium is not necessarily going to be all that stable, right? You're not necessarily going to condense and get the aminium. And if your R group here has proton sources associated with it, what will happen is any base, for example, and then maybe the excess amine that's in here, will do a reaction that's in a way, let's just put the amine there, for example. But again, it could be other things. Very E2 elimination-like, right? Sort of an elimination type reaction, except you're not losing anything. You're just sort of breaking the double bond. Okay. And in this molecule here, there's a name associated with it which is actually analogous to sort of the enol ketotautomers, right? And enol is that, right, as you guys sort of know, compared to the sort of the eno ketotautomer. R2. Right, if you think about it, enol, alkene, alcohol, enol, right? This is an amine, right? Right, so these molecules are called enamines. And we'll discuss enamines a little bit more in detail. They're very valuable, say, for example, with reactions we're going to learn soon called aldol reactions. You can actually have amine catalyze these aldol reactions, which is something that we'll discuss in a little bit. Okay, so with that, this next class what we'll do is we'll discuss a little bit about carboxylic acids, a little bit, I guess, and then we'll talk about enolate chemistry.
What if that carbon did not have hydrogens on it? Would it not be able to cause armor?
It would probably just go in reverse. Okay. Yeah. I mean, that's how people will often do enamine catalyzed chemistry. They'll have like if you actually look in the literature of enamine reactions, let's turn this off.